Hi, my name is Leen, and on this video I would like to talk about communicating with LoRa and LoRaWAN on the Renesas RA2E1 microcontroller. But first up, what is LoRa and LoRaWAN? Simply said, LoRa stands for long range. This is a communication technology that makes it possible to communicate over large distances with little power, but with a low data rate. LoRaWAN stands for LoRa Wide Area Network. This is a standardized protocol that makes use of LoRa technology. In the densely populated field of transmission standards, LoRa is placed in the low power and low data rate field. It operates in the license-free zone, but that doesn't mean it is without restrictions. For instance, you are only allowed to occupy a certain amount of airtime during the uplink and even less during the downlink times. Here you see the differences and also advantages of LoRaWAN compared to other technologies used in similar use cases. LoRaWAN is already widely adopted, while Sigfox is all but dead. Halo is very similar to Wi-Fi, but operates in the unlicensed band. However, it is still very new and has not yet proven itself. LTE-M and narrowband IoT operate in the licensed band and are much more power hungry. Typical user cases for LoRa and LoRaWAN are battery operated, low power and low data rate applications. You see LoRa often used in sensor and metering applications in remote locations where there is no wired power supply and the battery must last for a long time, or where a solar cell or some other type of energy harvesting is used for power. Here we see the basic structure of a LoRa or LoRaWAN system. On the left we see the LoRa sensor node. This is what we are talking about today. These typically consist of a low power microcontroller, a LoRa transceiver, some sensors and a power source like a battery or solar cell. These transmit periodically their data, typically once every 5 minutes or even less frequently, like once a day. Next we see the gateway. This device is typically a standard off-the-shelf purchase device from Dragino, Curlink, Miramico or any number of vendors. The gateway receives LoRa messages from the nodes and relays them to a LoRa network server or LNS via Ethernet, Wi-Fi or cellular connection. The messages are subsequently received by the LNS where the node has been registered. This can be Laureate, KPN, the Things Network or any number of organizations. These can be either public or private. Finally, the LNS can forward the data, the LoRa data, to an application server to be visualized and processed. Such an application server can be, for instance, Cayenne, Azure Web Services, Node-RED or any other. Now detailing Renesas' offering that targets the RA microcontroller family. The Renesas offering is based on 3 pillars. Low power. To control the LoRa transceiver, it is essential to have a very low power microcontroller to make a usable solution that can operate for several years on a small battery. The RA2E1 is such a low power microcontroller using less than 1 microamp in sleep mode. Easy to design. Renesas provides a full communication stack and several sample applications that can run out of the box. Your own application can control the LoRa transceiver with AT commands, thus creating a very low entry-level scenario for LoRa development. And easy to evaluate. The previously mentioned sample applications, or examples, run on a standard low-cost evaluation board and are fully documented and free of charge. Renesas also provides an easy-to-use protocol analysis tool. Here we have some details on the typical power consumption of the Renesas RA2E1 microcontroller, together with the Semtech LoRa receiver. Please note that the SX1261 is limited to 15 dBm transmit power in Europe, while the SX1262 can transmit up to 22 dBm in the US. Power consumption is of course higher at 22 dBm than at 15 dBm. This slide summarizes the power consumption scenarios for both the SX1261 for Europe and 1262 for the US use. Here we see a breakdown of the power profile of a typical use case. Most power is used for a very short period of time during the transmit phase and subsequently during the receive phase. The remainder of the time, the application is in low power or sleep mode. In this case, the period between transmissions is 3 minutes. You see that a typical lithium-ion battery of 1650 milliampere hours capacity would be able to power the application for over 21 years. If the interval was longer, for instance 5 or 15 minutes, the lifespan of the application would be even longer. Here we see a summary of the software offering from Renesas. Renesas provides both a LoRaWAN stack and also a separate RF driver that supports both LoRa and GFSK. To further support these, Renesas also provides in software an RF characteristic tool, an RF sniffer application and a power estimation tool. When using the LoRaWAN stack, the topology is as seen on an earlier slide, the one on the left here. However, when using just the RF driver, other topologies are also possible, such as a point-to-point connection or a star network. Use of the LoRaWAN stack is simplified by the addition of API functions to modify its configuration. The stack software is operating system independent and can also be used in a bare metal application. Here you have a summary of the LoRaWAN stack specifications. As already mentioned, the LoRaWAN stack is easy to interact by way of AT commands. The RF characteristics tools, called LPWA Studio, is a PC-based application that communicates with the RA2E1 microcontroller through a serial USB connection. The power evaluation tool is a customizable interactive Excel sheet. Now some details about the hardware being used. Here we see the boards being used. Central to the setup is the RA2E1 evaluation board in dark blue. In this block diagram, we can see the RA2E1. The RA2E1 includes the ARM M23 CPU core with up to 48 MHz frequency. Operating from 1.6 to 5.5 volts, the RA2E1 is offered with flash sizes ranging from 32 kilobytes to 128 kilobytes. The RA2E1 includes many efficient and unique features, including high-performance timers, capacitive touch, and safety and security blocks. Here we see the key benefits of the RA2E1. Starting with number 1, low power operation, which is crucial in this sort of application. Benefit 2, higher integration and optimized peripherals. Benefit 3, lower BOM cost. And benefit 4, ease of use. What more do you want? As already mentioned, the RA2E1 offers the best-in-class low power consumption in a 32-bit microcontroller. The sleep mode of this device stops CPU operation, reducing overall microcontroller current consumption by 80%. The software standby mode disables the microcontroller's on-chip functions, reducing power consumption to the lowest level possible. At the RA2E1, typical software standby current is 250 nanoamps, and RTC software standby current is 360 nanoamps. It also boasts a quick recovery time. From software standby mode and wake-up time in only 7.3 microseconds, using the high-speed on-chip oscillator. In snooze mode, the CPU is in the standby state, while the ADC conversion and serial communications are still enabled, so the CPU is activated only when required. This mode is excellent for battery-powered systems as it greatly reduces battery life. Greatly increases battery life, in fact. The Renesas RA development environment was designed to be for ease of use and as flexible as possible. The Renesas RA family are also supported by a wide range of on-chip debuggers, as you can see there. And it's currently supported by 3 different integrated development environments. As usual for ARM cores, the RA family is also supported by the GNU compiler, a free of charge GNU compiler, the ARM compiler, and the IRR compiler. And to make the development experience much more enjoyable, the RA family is supported by configuration tools for ease of use and ease of design. And finally, all RA product groups are supported by individual evaluation kits supporting onboard debuggers. The software examples and additional tools are grouped into a single package as shown. The LoRa sensor sample is a separate download. Now the hardware that we'll be using consists of the following boards. The RA2E1 fast prototyping board from Renesas, as you see here. The SX1261 Shield from Semtech. The USB to UART PMOD from Digilent. And finally, the HS3001 PMOD from Renesas to measure temperature and humidity. Now for the first example, I will not demonstrate anything because it's just a simple LoRa sample, which is further embellished on, or further built on, later on with the LoRa sensor sample project. Here we have the LoRa example number 2, which is a ping pong example. It's a simple application that is duplicated on 2 identical boards that transmit data to and fro. No further infrastructure such as a gateway or LNS is needed. The third LoRa example is a radio evaluation app, making use of the RA2E board with the SX1261 LoRa transceiver connected through a USB UART to a PC to sniff air traffic for LoRa packets and display them on the LPWA Studio application. I have now loaded the radio evaluation app into eSquare Studio, as you see here. Once again, we see the stacks configuration, the different drivers being used. The source code can be found here. Apps, radio evaluation app. It's all ready made, ready to go, so all we have to do is compile it and download it to the target. The target is still exactly the same configuration as what we had before. So download it to the target. And start it running. Next we start the LPWA Studio application and we connect to the device which is on the same COM port. Connect, and now it's connected. We have selected LoRa here. Frequency is 868 megahertz for Europe, and you've selected the public LoRaWAN. You can also select the private, but we're selecting the public. And first we want to have a look at what else is available in this area. Now I have several other nodes which are connected to my gateway, which are close by. So this application is just sniffing the airwaves at the moment. We can have a look at my gateway, what my gateway is receiving at the moment, and we can start sniffing. We're scanning the frequency from 868 megahertz to 870 megahertz in steps of 50 megahertz or 50 kilohertz, and we're doing 30 scans. And we have to select GFSK in this case, and we start scanning. And we'll just wait for some data to come in. So what you see here is the red line is the RSSI max, and the blue line is the RSSI baseline. So here we've just received some data, another one, and you slowly see a peak rising up above the noise level. And that is at 867,500 thereabouts. So that concludes this scan, and we see that we have a nice peak here at 867.5 with an RSSI of minus 112 and an RSSI max of 44, minus 44 dBm. If we then go to receive, we can go into sniffer mode, where we select sniffer and click on start, and then wait for a short period of time for data to come in. It'll sniff for LoRa transmissions in the immediate ether, so not going through a gateway or whatever. So we can monitor our local gateway here, which is also a sort of sniffer, to see when data comes in. We'll stop and come back in a few minutes. So after several minutes, we see that some data has come in, and we can see that some errors have also arrived. So the listings in red have an error. We get rid of this window. We can see the RSSI values varying. We can zoom in or out. And if, we'll just stop it, if you set the app key in this field here, you can actually decode the data, or decode the data if you can actually see the data. So that could also be helpful in some cases.
And finally, the LoRa example number 4, which is the LoRa sensor sample application. This is the most elaborate example in the LoRa sensor sample kit that makes use of the complete hardware setup for both temperature and humidity on an application server, and in this case, Cayenne. The example as presented in the tutorial makes use of a Curlink gateway and LoRaWAN as LNS. However, In the following demo, I will use a Dragino gateway and TTN as the LNS. The example is fully documented and can be downloaded from the link shown here. Once the hardware has been set up and powered, and subsequently the compiled project has been downloaded to the target and started, the connection must be initialized with these 7 AT commands listed here. Finally, the transmission interval and manual start setting are sent to the target and it is started. Here I have loaded the LoRa sensor sample into eSquare Studio. You see that the project has been selected here on the left, and we're now looking at the summary of the project. The BSP tab showing the FSP version, the target board and the actual device being targeted. The clocks tab, pins tab, interrupts, and here the stacks tab to show all of the different stacks that have been implemented in this application. This all comes as is and no further modifications are required. First I will compile the project, 0 errors and 0 warnings, and I will subsequently program it into the target. Once I've connected it, press debug and it will load into the end target, which I have done in the meantime. And now you see the target down here with the evaluation board, the blue evaluation board here, the LoRa sensor board green here, the USB to UART board from Digilent connected to the PC here, and here we have a temperature and humidity sensor also connected to a PMOD. This cable goes to the debug and subsequently to the PC. If we configure the target, we can do that with AT commands. We can LoRa with a number of instructions, 7 instructions all up, detailed in the tutorial. And we also have to add the dev UI. Blah blah blah. I'll skip that all now. Because I've done that previously. We don't have to show you my secret code. And now we will join the device to the internet. First I'll open my things stack, the LNS. And we'll go to the board that I've already registered on the LNS, and here we see the live data. At the moment we don't see any actual data, but once we join, so AT plus join, we see that we have joined. I'll just send some test data, send hex, and we'll just enter some fake data. Now you can see, yep, that it has received this data. Now in this actual application, we're monitoring data, temperature and humidity data from the sensor. And to start that application, we have to instruct it to transmit data every 300 seconds. Then we have to start the sensor application. And it will now transmit data every 5 minutes or 300 seconds. We'll come back in a few minutes and see what has happened. Now a number of minutes have passed and we see that some data has been sent. If we have a look here, I'll just change the formatting here. We can see that the initial join was done here at 11:33, and then 5 minutes later we've received the first message with a dummy payload, which you see duplicated here on the terminal window. And then 5 minutes later again, we see the first actual measurement. Relative humidity 41.5% and temperature 20.6 degrees Celsius. And this has been sent in. Now we get a second message in 5 minutes later again. Temperatures, well, the humidity's risen 0.5%, temperature's risen 1/10 of a degree. The message is sent in Cayenne LPP format, and we have configured that in the things stack by clicking on payload formatters, the up link, and there we have selected Cayenne LPP. Cayenne LPP is a particular syntax given to the data that is being sent, and from that can be derived the type of data and the value of the data, which makes life a lot easier. It's fully documented on this link here, which you can access from the things stack the console page. We have also configured a Cayenne application visualizer, conform the instructions in the tutorial, and we can now see that the actual data has been displayed. 42% humidity and 20.7 degrees Celsius, as well as the signal to noise ratio and the signal strength. This is the overview. You can actually see the data in some more detail here. The live data over a period of time. This makes it very intuitive.
Here you find the web links to the LoRa solutions on the Renesas site. Download the LoRaWAN samples and examples and implement these features in your next application. In closing, I would like to thank you for your attention, and if you have any questions or recommendations for future videos, don't hesitate to contact me on this address. Thank you for your time.